Organic reactions, type of organic reactions and mechanisms. So, till now, in our previous discussions, we have seen about the generation or the production of the intermediate of organic reactions. So, they can be either carbon free radicals, carbocation, a positively charged carbon, a carbanion, or a negatively charged carbon ion, and the different types of effects produced in organic reactions. And these can be the inductive effect, the positive and negative inductive effect, the mesomeric effect, the positive and negative mesomeric effect, the resonance effect, the positive and negative resonance effect, and the hyperconjugation effects. So now henceforth we will be discussing about the fate of these reaction intermediates and the effects in the following organic reactions. And, and these organic reactions are classified as substitution reactions, addition reactions, elimination reactions, rearrangement reactions. We will discuss each one individually in our coming slides. So, substitution reaction is the first reaction, and this is also called as the displacement reaction. So, in this type of reactions, an atom or a group of atom present in the substrate is replaced by another atom or a group of atoms. In the below example, CH3Cl, that is chloromethane. So, when chloromethane, a hydrocarbon, reacts with sodium hydroxide, the product we get is methyl alcohol or methanol, CH3OH plus sodium chloride. The chlorine of the chloromethane is displaced by the hydroxyl group of the base, that is sodium hydroxide, to form the methanol, and sodium reacts with chlorine, eliminated chlorine or displaced chlorine to form the salt sodium chloride. Second is the addition reaction. So, addition reactions, we find the atoms or groups of atoms are added to the unsaturated system. So, this type of reaction can take place in hydrocarbons or in organic compounds, always having a carbon carbon double bond, which means this involve the pi electrons. The pi electrons are overlapping laterally to form the pi bond. They do not combine with any other outside atom or group. Thus, one pi electron of one carbon and the other pi electron of the other carbon overlap laterally to form the pi bond, which is weak bond, and thus represents the double bond in unsaturated carbon compounds. So in the below example, CH2 double bond CH2, that is ene, reacts with hydrogen in presence of a nickel catalyst to form the ethane molecule. CH3 single bond CH3 is ethane, a saturated organic compound. So the hydrogen here shares one electron each with each carbon, thereby forming a single covalent bond. The third type of reaction is the elimination reaction. Here, two atoms or groups are removed from same carbon atom or from adjacent carbon atoms in a molecule. I repeat, your atoms or groups are removed either from the same carbon atom or from a different carbon atoms in a molecule. In the example, ethyl chloride, that is CH3 CH2 Cl, ethyl chloride, when it reacts with alcoholic potash, the compound formed is ethene plus potassium chloride plus water. The compound is chloroethane. It is chloroethane reacts with alcoholic potash to form ethane, potassium chloride, and water. So the chloride molecule from the first carbon atom reacts with potassium to form potassium chloride, and the hydrogen from the second carbon atom reacts with OH minus to give you water molecule. I repeat, the chloride, the Cl atom from the first carbon atom reacts with K plus to form KCl, and the hydrogen of CH3, that is the second carbon, reacts with OH minus to form H2O. Such type of reactions are called as the elimination reactions. And the fourth type is the rearrangement reaction. So here we see the migration of an atom or a group of atom from one carbon to another carbon within the same molecule. Migration of atom, or it can be groups of atoms from one carbon to another carbon within the same molecule. In the below example, we see the compound that is N-pentane. Pentane is a molecule having 5 carbon atoms having joined by single covalent bond. So it is CH3, CH2, 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 CH3 in presence of a catalyst like anhydrous aluminum trichloride, that is anhydrous AlCl3, and heat. The compound formed is 2-methyl butane. The compound formed is 2-methyl butane. It is an isomer of the reactant or the substrate. It is an isomer of the reactant or the substrate. So we have already studied that isomers are the compounds containing same number of carbon atoms and hydrogen atoms but differ in their structure. So here the N-pentane, that is a normal pentane, is being converted to 2-methyl butane, which is also commonly called as isopentane, which is also commonly called as isopentane. So here we find there is rearrangement within the same molecules. Thus, these four types of reactions are very much essential in studying the organic reactions of our further classes. Now, this is a discussion about the organic chemistry chapter, unit 10 of second year syllabus. I repeat, unit 10 of second year syllabus, that is haloalkanes and haloarenes. So halo means they are generally referred to as fluorine, chlorine, bromine, and iodine. These are the group 17 elements found in the periodic table to the extreme right side of the modern periodic table. So they together represent group 17 and they are commonly called as the halogen family. They're commonly called as halogen family. These halogens, if they are attached to either an alkane or an alkene or an alkyne, they are called as haloalkanes or haloarenes. So, the replacement of hydrogen atoms from a hydrocarbon, which can be either aliphatic or aromatic, by a halogen atom results in the formation of an alkyl radical, what we call it as the haloalkane or commonly called as alkyl halide. So, haloalkanes contain halogen atoms attached to the sp3 carbon atom of an alkyl group, whereas haloarenes are the compounds which contain halogen atoms attached to a sp2 hybridized carbon atoms of an aryl group. I mean to say, if the hydrogen is removed from alkanes and replaced by halogen, then the compound formed by the displacement or substitution of one hydrogen from alkane by the halogen, the compound formed, we call it as haloalkanes, and the carbon exists in sp3 hybridized state. Now, in compounds where the carbon carbon are joined by a double bond, then one of the hydrogen atom, if it is replaced by a halogen, and the compound formed now contain halogen atoms attached to carbon atom, which is joined to another carbon atom through double bond, then such compounds are called as haloarenes, where the carbon now exists in arene state or sp2 hybridized states. So these class of compounds, why we have to study this haloalkanes and haloarenes, and what are the applications of these compounds that we find in our daily life, so that the industry produces them in large quantities. So since they are used in our day to day lives, we have to study about them. These are used as solvents for relatively non-polar compounds, and they are also used as starting materials for the synthesis of wide range of organic compounds. For example, the chlorine containing antibiotic chloramphenicol, which is produced by soil microorganism, is very effective for the treatment of typhoid fever. So the chloramphenicol produced by microorganism is in very small quantity, and no doubt we need this antibiotic in larger amounts for treating the typhoid fever. So in such cases this can be synthesized in the industry, and hence we will have to study them. And synthetic halogens like chloroquine. So, chloroquine is generally used in the treatment of malaria, which is of late in more demand in the world now. Halothane is used in anesthetic drug during surgeries. So, all these compounds are hydrocarbons in which one or more atoms are removed and are replaced or displaced or substituted by halogens. I repeat, and these halogens can be fluorine, chlorine, bromine, or iodine. So, we shall now study these important compounds whose methods of preparation, physical properties, chemical properties, and uses are very, very important. First, is we will discuss about the classification, and there are n number of ways of classifying any compound, and the methods adopted are different. So, here for our simplification, we will study one method based on the number of halogen atoms. So, based on the number of halogen atoms displaced or substituted, the haloalkanes or haloarenes can be classified as mono, di, or polyhalogen compounds. That is depending upon whether the carbon attached contains one halogen, two halogen, or more halogen atoms in their structures. Here in the below example, we find this is ethane C2H6. I repeat, C2H6 is ethane. We have removed or displaced or substituted one hydrogen and replaced it with only one halogen, and hence it is called as monohaloalkane. If X is chlorine, it is chloroethane. Mono, chloro, and the alkane is ethane. The second compound is CH2X, CH2X. So here two hydrogen atoms from CH3, CH3. Two hydrogen atoms are removed and displaced by two halogen atoms, and that is why they are called as dihaloalkene, that is dichloroethane. If the alkane is ethane, it is dichloroethane. The halogen is chlorine. And then the example CH2X, CHX, CH2X. So here three hydrogen atoms, sorry, three hydrogen atoms are replaced by three halogens. It is the molecule propane. Three carbon containing compound is propane. So CH3 single bond CH2 single bond CH3 is propane, and three hydrogen atoms each carbon atom has been removed and replaced by halogen, and hence these compounds are called as trihaloalkane. So it is trichloropropane. So in the next example, a benzene ring C6H6, one hydrogen is removed and replaced by halogen. So it is monohaloarene. In the next example, it is C6H6 minus 2 hydrogen, it is C6H4X2. So it is dihaloarene. In the third example, C6H6 minus 3 hydrogens will give you C6H3X3, and the compound is trihaloarene. So arenes are compounds containing generally benzene ring or a double bonded carbon atom containing compounds. So monohalo compounds may be further classified according to the hybridization of the carbon atom to which the halogen is attached. So alkyl halides or haloalkanes are generally represented by Rx. Are generally represented by Rx. So in alkyl halides, the halogen atom is bounded to an alkyl group. They form a homologous series represented by Cn H2n plus 1 X. Now it is H2n plus 1 X, which are further classified as primary, secondary, or tertiary according to the nature of carbon to which halogen is attached. Now, in the above slide, we have studied the examples and we find they are monohalogen compounds, dihalogen compounds, and trihalogen compounds is one method of classifying the haloalkanes and haloarenes. Now, the second method is classifying based on the degree of carbon atom. So, here we will get to know whether the halogen is attached to 1 degree carbon atom or 2 degree carbon atom or 3 degree carbon atom. So, according to the nature of carbon atom, the haloalkanes are further classified. In alkyl halides, the halogen is bounded to an alkyl group. They form a homologous series CnH2n plus 1x. First one is allylic halides. So these are the compounds in which the halogen atom is bounded to an sp3 hybridized carbon atom. Next to carbon-carbon double bond or to an allylic carbon. And benzylic halides, these are the compounds in which the halogen atom is bounded to an sp3 hybridized carbon atom lying next to an aromatic compound. The example, that is RCH2X, the carbon now exists in 1 degree, which means the carbon is attached to only one carbon exists, and this one carbon is attached to two hydrogens and a halogen atom and another alkyl group. It is called as 1 degree carbon atom. In secondary carbon atom, we see the carbon is attached to two different R groups, a hydrogen and a halogen. And in tertiary or 3 degree, we find carbon that is attached to three different R groups and a halogen. The other example, we find a carbon is attached to a double bond and the CH3 group, one hydrogen is replaced by a halogen, which is similar to those in case of benzene molecules. And in the third one, 1 degree, where a benzene molecule CH2 group is attached and halogen is attached to that. So here we find the carbon now exists in 1 degree. Carbon now exists in 1 degree. And in the next example, benzene, that carbon, the two hydrogens are replaced by the R groups. Now that compound will be a 2 degree and a 3 degree compound. First one is vinylic halides. So these are the compounds in which the halogen atom is bounded to sp2 hybridized carbon atom. They are called as vinylic. That means the halogen must be attached to the carbon which should be attached to the next carbon through a carbon carbon double bond. Aryl halides. These are the compounds in which the halogen atom is bonded to sp2 hybridized carbon atom, like the benzene ring, where we find the halogen atom is directly attached to the carbon, which is bound to another carbon through a carbon carbon double bond.